All right, so let's take a look at the solutions of the practice problems 28, our 11.9 representations of functions as power series. So remember that we're always starting from the same place. So we're letting our g of x be the 1 over 1 minus x. And I want to try to build the function that's in f. First thing I'm going to do is build the denominator. So I have 1 minus x for g of x, but I want 1 minus x to the fourth. So what that means is that I want to plug in x to the fourth in place of the x. So that's going to give me 1 minus x to the fourth. Then in order to get the 3x in top, I'm just going to go ahead and multiply that. So I'm going to take 3x times g of x to the fourth to get 3x over 1 minus x to the fourth. So again, what we did in order to get from g of x to f of x, we have to take 3x times g of x to the fourth. So if I apply that same procedure to the summation or the power series equivalents of g of x, then I'll end up with the power series representation for f of x. So that means I start out with n equals 0 to infinity of x to the n, which is my g of x, and I'm going to turn that into 3 times x times g of x to the fourth. So first thing I'm going to do is to find g of x to the fourth, and that means I'm going to plug in x to the fourth for my x. And that's going to give me n equals 0 to infinity of x to the 4n. And the last thing I do is I'm going to multiply it by 3x. So that means I'm going to take n equals 0 to infinity and multiply it by 3x. So 3x times x to the 4n. And if I want to simplify that, I leave the 3, but I can combine the x's. So it's x to the 4n plus 1 extra. So there's my power series representation for number 1. For number 2, I've got a couple, okay, just wondering. All right, for number 2, same thing. We're going to start from g of x equals 1 over 1 minus x. And so I want to build f of x. So the first thing I need to do is make that my denominator go from 1 minus x to x plus 4. Now, one of the ways that you can do that, if you're not sure, is to replace the x in g of x with a u and set up the denominator. So I want 1 minus u to be equal to x plus 4. And so that way I can subtract the 1. So negative u is x plus 3 if I subtract 1 from both sides. And then take the opposite. So u is equal to negative x minus 3. So that's what I want to plug in here. I want g of negative x minus 3. And you can see that when I do that, I'm going to get positive x and positive 3 plus the 1 gives me the 1 over x plus 4. And then in order to get the numerator, we're going to go ahead and multiply by x squared. And that will give me the x squared over x plus 4. So if we do the same thing and apply it to our series version, so for g of x, we have sum n equals 0 to infinity of x to the n. So then what I want to do in order to represent the 1 over x to the fourth, we replace the x with negative x minus 3. So negative x minus 3 to the n. And then we multiply it by x squared. So this is n equals 0 times infinity x squared times negative x minus 3 to the n. And that's my power series representation. All right, notice this one. Let's see what happens here. So I'm trying to go from g of x, which is 1 over 1 minus x, to get the one up above. Now, I know I've experienced with the last one in the practice problems where we have parentheses of 1 minus x squared in the bottom, and that was the derivative. So this is cubed, so maybe we need more than one derivative. So if I think about this as 1 minus x to the negative 1, then the derivative of g is negative 1 minus x to the negative 2 times negative 1. Don't forget the chain rule there, which is 1 minus x to the negative 2. Okay, so that gives me a negative 2 power, but I need a negative 3 power. So let's try taking the second derivative. That's going to give me negative 2 times 1 minus x to the negative 3, so that's good, times negative 1, so that cancels. So that gives me 2 times 1 minus x to the negative 3, which is really 2 over 1 minus x quantity cubed. Which is actually really, really good because not only now do I have this part, but I also have the 2. So the only thing that I'm missing is the x. So all I have to do then is multiply this by x. So then I want x times g double prime of x to give me the 2x over 1 minus x quantity cubed. So now we just need to replicate that with the power series. So we know our power series, our g of x, is n equals 0 to infinity of x to the n. And I want to take two derivatives. So g prime, remember that when you take derivatives, we're going to lose a term. So this will go from n equals 0 to n equals 1. And it's n times x to the n minus 1. Right? You bring down your exponent, decrease your exponent by 1. Then we want the second derivative. So now I want the derivative of the derivative. Again, I'm going to lose a term. So I'm going to go from n equals 1 to n equals 2. And I'm going to bring down again. So I leave the n, focus on the x to the n minus 1. So I'm going to multiply by n minus 1 and decrease my exponent by 1 again. So it's going to go to n minus 2. And then the last thing I have to do is multiply through by the x. So xg double prime of x, which, by the way, is what was over here, is going to be sum n equals 2 to infinity, n times n minus 1, x to the n minus 2, and I'm going to multiply it by an x. So what you can actually do is to combine that x with the other x's and make it n times n minus 1. And I'm going to add 1 to my n minus 2. So n minus 2 plus 1 is n minus 1. And so that's my power series representation for number 3. For number 4, anytime we see an ln, we're thinking integrals. But in order to take the integral and get the natural log of 1 plus 2x, I'm going to need to get 1 plus 2x in the denominator before I take the integral. So let's start with g of x. Our g of x, we know, is 1 over 1 minus x. So I want to make it 1 plus 2x. So what I'm going to do is replace my x with a negative 2x. That will give me 1 plus 2x in the denominator. Okay, so now if I take the integral, that's what's going to give me the ln. Now we may have to mess around with this a little bit to compensate because I think something else is going to pop out of here. So in order to take the integral of g of negative 2x dx, we integrate 1 plus 2x to the negative 1, which really doesn't matter. I can leave it as 1 over 1 plus 2x dx. Now I would use up here for the bottom. So 1 plus 2x du is 2 dx. And so 1/2 du is dx. So when we go to find the antiderivative here, this is integral of 1 over u times 1/2 du. And so this is 1/2 natural log of u, which is 1 plus 2x. So it's very close to what I wanted, but I have an extra 1/2 here. In order to get rid of the 1/2, I'm going to have to multiply everything by 2. So I have to multiply by 2 here, by 2 here, by 2 here, and by 2 here. And that will cancel these two out and give me what I'm looking for, which is the natural log of 1 plus 2x. So what I'm doing in order to get that is right here. I'm taking 2 times the integral of g of negative 2x. So I want to do the exact same thing with my power series representation. So my power series representation for g of x is sum n equals 0 to infinity of x to the n. So the first thing I do is get g of negative 2x. So I'm going to replace my x with a negative 2x. So n equals 0 to infinity, negative 2x to the n. And I'm going to split that up just so that I can see it. And I'm going to make it negative 2 to the n and x to the n. Right? That way I separate the constant away from the variable part. Because the next thing that I want to do is I want to integrate this. Well, I want to double it and integrate it. So if we double it, so 2 times g of negative 2x is going to give me n equals 0 to infinity of 2 times negative 2 to the n, x to the n. Now, I don't want to put the 2 inside with the parentheses because it's not a negative 2. If it were a negative 2, then I could easily put that inside and make it n plus 1. But I would have to separate out the negative 1 from the 2 and put the extra 2 with the 2 and not the negative 1. So I'm going to leave it as is. Then we're going to integrate it. So integral of 2g of negative 2x. So I can just integrate the 2 times negative 2 to the n times x to the n dx. And what that turns out to be, when we integrate, we don't lose terms. And by the way, we know the plus c is going to be 0 here because we don't have any constant term added on to our ln. The number part, we leave alone. So 2 times negative 2 to the n stays. And I'm only going to differentiate the x. So I'm going to bring down the n and decrease the exponent by 1. Scratch that. No, I'm not. I'm integrating here. So I'm going to add 1 to the exponent and make it x to the n plus 1 and divide by n plus 1. And that will give me my power series representation.